I'd like to welcome you to this first recording in the 2013 presentation of the module MSD 210 Dynamics. I'm Professor Nico Tron, and on this slide I'm giving you my contact details. This also appears in the study guide, and it also appears on ClickUp. You are most welcome to come to my office to ask me questions or to discuss problems that you may have with this module. Myself and my fellow lecturers will publish office hours on our doors and on ClickUp. And we'd like you to use this office hours. During the office hours, you can come unannounced to our offices. You can just pitch there, and then if there's nobody else standing in line in front of you, you can ask me a question and I'll try to resolve the problem for you. Outside of the office hours, we prefer that you make an appointment to see us. This is most easily done by sending an email. That's why my email address is given here. Send me an email and suggest a time for a meeting. My timetable is quite often less cluttered than yours, so it's perhaps easier if you suggest a time. If that time doesn't suit me, I'll then try to indicate an alternative time. Before we publish the office hours, you're most welcome to come to my office at any time during the normal day, Monday to Friday from 8 to 5 in the afternoon. If you catch me in the office, I'll help you. This is now up to the point in time when the office hours for this semester is announced. I'd like to spend a minute or two on the prescribed textbook for this module. Miriam & Craig's Engineering Mechanics Dynamics. You'll note that two editions are indicated on this slide, the 6th and the 7th. The 7th is published this year. We were not aware of the fact that the publisher, John Wiley, is bringing out the 7th edition, and because of that, the book that is prescribed on satextbooks.net is still the 6th edition. But the fact that they've now brought out the 7th edition may mean that there may not be sufficient copies available of the 6th edition for everybody to buy. And because of that, we are really forced to use both editions this year. So both editions will be valid in this course, in this module. You can buy either the 6th or the 7th edition, whichever one you can lay your hands on. I know that the local bookstores have ordered both the 6th and the 7th edition, but not sufficient numbers of either one so that we can stick to either edition. It's important that you use the SI version. Both editions are available in the SI version, and this is important because there is also a non-SI version available. And the non-SI version has problems and examples in which imperial units are used, not only SI units. Some problems are on SI units, some on imperial units. We don't like that. We prefer the SI version in which all the problems and all the examples are in SI units. If you buy the book using this ISBN number, you will get the SI version. I would like to skip over this slide. We're going to pay attention to this during the class presentation. And we are next going to look at a little bit of revision. But before I get to that, I'd like to switch off the video camera in order to save on file space. And let me also make the slide full screen. We're going to do revision on dot and cross products. Now we know that you've been introduced to this in your mathematics course, mathematics modules last year, but both dot product and the cross product are very important in the study of dynamics. And because of that, we decided to start off the dynamics presentation by doing revision of these two products of vectors. Now let's start off with the dot product. The dot product is also called the scalar product, and to see this, let's consider two vectors A and B. Now let me interrupt myself for a moment. I'd like to just point out the notation that we're using here. You'll see that the vector A is indicated with a symbol A, of course, but with a little arrow with a single hook at the top. You are also welcome to use an arrow with two hooks, the normal conventional arrow. But in our presentation, we'll use this arrow with a single hook. The important point is that you do indicate the vector as a vector in some other way. You can also use just a bar, but we prefer that you do not use that, because the bar quite often in mathematics is used to signify something differently. But you should definitely not omit something like an arrow over the symbol. Because if you do omit this arrow symbol above the letter with which you indicate the vector, we will read this as a scalar quantity, and there's a vast difference between a vector and a scalar quantity. So if you write in your test and exam a vector and you indicate it with the alphabetical symbol, but you do not include the arrow overhead, we will penalize you for that, because then what you will be writing most probably will be nonsense. So it's important. Perhaps I should just mention that in textbooks, vectors are quite often indicated without the arrow, but then they use a bold symbol to indicate that it's a vector. But in writing, it's very difficult to use bold symbols and still have a clear distinction between a vector and a scalar. And because of that, since we deal with handwriting in a module like this, especially during the students' answer of tests and problems and assignments and in the examination, we cannot rely on this bold notation to indicate the vector. We need to have the arrow overhead. Okay, so we have two vectors, A and B, and we express both of them in terms of their components in the X, Y, and Z direction. So I'm using the standard I, J, and K notation for where I is the unit vector in the X direction, J the unit vector in the Y direction, K the unit vector in the Z direction of a rectangular coordinate system. We're working with these vectors in 3 dimensions. The second vector B is also expressed like the vector A in terms of its components in the X, Y, and Z direction. Now the mathematical definition of the dot product is given by this expression, and what we can see from this is that the dot product is simply the sum of the products of the components of the two vectors. In other words, it's the component in the X direction of A times the component of the X in the X direction of B, plus the component in the Y direction of A, its product with the component in the Y direction of B, plus then lastly the product of the Z components, AZ and BZ. Note that the components are scalar quantities. If I multiply the component with the unit vector, this product becomes a vector. But the AX is just a scalar quantity, and so is BX. So the product of these two scalars, of course, is also scalar. And so what we have is the sum of 3 scalars. And because of that, we can see that this whole result is a scalar quantity. It's not a vector. That is why the dot product is also called the scalar product. Note also that the dot product satisfies the commutative law. In other words, I can reverse the sequence of the two factors in this product, and the result will still be the same. A dot B is the same as B dot A. Let's look at an example. Let's consider the vector R, which is defined as 5i plus 6j plus 3k. And in this case, we do not worry too much about the units of this. R can be any vector. It can be a displacement vector, or it can be a force vector, whatever vector you can think of. But let's see how we represent this vector R. And this vector R is the blue vector in this sketch on the right-hand side. I'm going to just enlarge this. The vector R is represented here as a vector starting at the origin of the X, Y, Z axis system. You can now perhaps more clearly see the three axes, the X, Y, and Z axes. So this vector starts at the origin and it ends at some other point in 3 dimensions. Of course, it's a 3-dimensional representation on a 2-dimensional plane here. But so this point here represents a point in the X, Y, Z axis system with coordinates 5 in the X, 6 in the Y, and 3 in the Z direction. So this is my vector R. Now, let's also then consider the dot product of this vector R with the unit vector I, the unit vector in the X direction. If we use this definition, of course, we can clearly see the 3 components of R in the 3 directions. The question is, what are the components of the vector I? Well, the vector I being a unit vector in the X direction means that its component in the X direction is 1. That is its length. And since it's aligned purely in the X direction, its length must be the same as its component in the X direction. And its components in the Y and the Z directions are 0. And because of that, we can then write this expression for the dot product between R and I, and we see that we end up with a value of 5, since the contributions of this second and third products are both 0. In the same way, we can now calculate the dot product between the vector R, the blue vector, and the unit vector in the J direction. And if we do now, of course, the X component of J and the Z component of J is 0, but its Y component is 1, and this means that the first and third terms are 0, the second term is 6, and that is the result that we get. Likewise, if we calculate the dot product between R and the unit vector in the Z direction K, we end up with a value of 3. This then leads us to a conclusion that if we want to calculate the component of a vector in any of the 3 axis directions, we merely need to calculate the dot product of the vector with the unit vector in that direction. We can generalize this, and I'm not going to show this as a rigorous mathematical proof, but I'm just going to show this by way of an example, 2 further examples. But the generalization really reads like this. To calculate the component of a vector in a certain direction, one merely needs to calculate the dot product of the vector with the unit vector in the required direction. Now, this is a very useful conclusion for us in dynamics, because quite often we need to know the component of a vector in a certain direction, where this certain direction may not necessarily be a coordinate axis direction. And if we then want to calculate the component of a vector in that direction, we merely need to calculate a unit vector in the required direction, and then calculate the dot product of the vector in question with that unit vector to give us the component required. Let's investigate this a little bit further. Let's once again, in example 2, consider our blue vector R, the same as before, but we consider a second vector D, given by this expression. Now, I claim at the bottom here that D is a unit vector in the XZ plane. Now, why do I say that? Now, let's quickly look at, and I'm going to blow up the sketch again. Let's look at the vector starting at the origin and ending at this point here with coordinates 5 in the X direction, 3 in the z direction, but the point in the xz plane. In other words, the point where, of which the y coordinate is 0. I can, of course, define a vector between the origin and this point. I haven't actually drawn it in the sketch, but you can define that vector in your mind's eye. And we can for now call this the unnamed vector. This vector, of course, will be validly described as 5i plus 3k. 5i plus 3k. Now, I'd like to now next define a unit vector in this direction. Now, you need to remember that to define a unit vector in any specific direction, I merely need to take a vector in that direction and divide it by its own length. The moment I divide a vector by its own length, I end up with a unit vector. And if I divide, remember that the length doesn't have direction, the length is scalar. So dividing a vector by its length doesn't change its direction. It's still in the same direction. So if I divide this vector between the origin and this point by its own length, I'll have a unit vector in this length, in this direction. And this unit vector, I'm trying to represent in this sketch by this red arrow. This, of course, implies that the distance from there to there will be larger than 1, since I've drawn the red arrow slightly shorter. Let's see whether that is true. Let's first of all calculate the length of this line, or the magnitude of the vector 5i plus 3k. And by Pythagoras, it's of course 25 plus 9, or the square root of 25 plus 9. In other words, the square root of 5 squared plus 3 squared. So that is the square root of 34. So the length of this vector is the square root of 34. If I now go back to the previous slide, I see that I define the vector d as 5 divided by the square root of 34 in the I direction, and 3 divided by the square root of 34 in the k direction. So this is the vector, the unnamed vector, divided by its length, and hence I can claim that this vector d is a unit vector in the direction from the origin towards this point here. Now, if I calculate the dot product between r and d, I find that since the vector d doesn't have a component in the j direction, the second term in the dot product calculation is 0. But the first term will be the product between 5 and 5 divided by 34, which is 25 over the square root of 34. And the third term will be the product of 3 with 3 over the square root of 34, which is 9 over the square root of 34. And if I then add this together, I get a value of the square root of 34. And so I see then that the dot product of the vector r with a unit vector in this direction is the square root of 34, which is the length of this unnamed vector, but which is also the component of the vector r in this direction. So with this example, I've shown that the component of r in the direction of d is the square root of 34, the square root of 34, and this is exactly the same as the vector r dot the vector d, the unit vector in the direction required. I'd like to now look at a third example where we're going to look at a unit vector which I've indicated with this green arrow, a unit vector E in exactly the opposite direction as the vector D. So the unit vector E will be the same as this, except that there will be a minus sign there and there. So this is shown here. If I now calculate the dot product between R and the unit vector E, I get minus the square root of 34. And I come to the conclusion that the component of the vector R in the direction of E is minus the square root of 34. And that is the same as the dot product between R and the unit vector E. I would now like to look at two further examples to illustrate a different point. Let's consider the same vector R, but a second vector G, which is defined like this. If we now calculate the dot product between R and G, it's quite simple, and it turns out to be -6. If we now, in example 5, look once again at the same vector R, but a different vector P, which happens to be the same as the vector G, except that it doesn't have a component in the Z direction. And if we now calculate the dot product between R and P, we find that we end up with a value of 0. And this raises the question, what does this mean? What does it mean when the dot product of two vectors is equal to 0? Now, one possible explanation for having a 0 dot product is that either one of the two vectors may be a 0 vector. It's true that in general, if either R or P is a 0 vector, the dot product between the two will be a 0 vector, will be a 0 value. Of course, the dot product being a scalar, it will be just the value 0. That is the trivial case. It's true, but we do not really mind too much about this case. We'd like to know what happens, like in this example 5, where clearly neither R nor P are 0 vectors, yet the dot product is 0. What does that mean? Now, I'm stating here that if the dot product between the vector R and the vector P is 0, while it's known that the length of the vector R is not equal to 0 and the length of the vector P is also not equal to 0, then the two vectors are perpendicular to one another. Stating that the length is unequal to 0 is the same as saying that it is a non-zero vector. A 0 vector always has a length of 0. Can we prove this? It's not too difficult to prove this, because if the dot product between the vectors R and P is 0, and we know that the length of P is unequal to 0, then we can divide this dot product by the scalar length of the vector P. And if we divide this dot product through P, it means that we can divide well, either R or P in the product by this scalar quantity, and I've selected here to divide P by the scalar quantity. So if R dot P, the vector R dot the vector P is equal to 0, that means that the vector R dot the vector P divided by its length must also be 0. But the vector P divided by its length is a unit vector. So what we see here is that we've concluded that the dot product between R and the unit vector in the direction P is equal to 0. On the left-hand side here, we have an expression for the component of R in the direction of P by virtue of what we've proven earlier today. So this means that the component of R in the direction of P is 0. And because of that, we can conclude that the vector R must be perpendicular to the vector P since the component of R in the direction of P is 0. Now this concludes the revision of the dot product, and I'm going to stop the recording now and continue with a separate recording for the cross product.